So I just want to remind you, there's been some beautiful talks this week already about shifted structures, Pavel, and then today, Tony gave a really wonderful talk. So I'll be using a lot of their terminologies, but I want to say a few words about where shifted structures come up from my point of view. So let Y be any sort of manifold in quotes here. This could be like some infinite dimensional thing. For me, in practice, it's going to be the space of fields of some theory. And I'm going to take a functional on Y, call it S. This is like the action functional in physics. And sort of very basic starting fact for me is that the derived critical locus of S, this is a derived space which enhances the usual critical locus, which is just where the derivative of S is 0, sitting inside of Y, is a -1 shifted symplectic space. And the algebra of functions on this shifted symplectic space is equipped with a Poisson bracket of cohomological degree +1. And I'll call this brackets here. I think Pavel had mentioned in his talk, this is sometimes called the BV bracket. So what's going on here is I'm describing a field theory in what's called the classical BV formalism. And more generally, the sort of data that you want to start with in this formalism is a shifted symplectic space X, which is playing the role of this critical locus, and an action functional S, which is a function on X, which satisfies this equation. So it Poisson commutes with itself, which is a non-trivial equation here because of the shifted degrees. This is sometimes called the classical master equation. So in the case that X is some linear space, then it's typical to decompose this action into a quadratic part and a part which is at least cubic. So I is what's called the interaction. And the quadratic part always looks like this. So it's the shifted symplectic form evaluated on the field phi and the field q times phi, where q is just some differential here. So q will be a differential on this linear space X. And this functional, it's good to point out, is just a degree 0 thing. So I have shifted structures around, but S is just a degree 0 function. So the example one should always give is the following. So let M be a 3-manifold, G is a Lie algebra. I look at, sorry, that should say X. So this is the de Rham forms on the 3-manifold with values in G shifted down by 1. There's a shifted symplectic form on this space, which is just wedging and integrating. Here I'm assuming G is equipped with a invariant metric, and I'm using that to define this shifted symplectic structure. This is a -1 shifted symplectic structure. There's a well-known action functional I can construct using this, where I let the quadratic part be given basically just by the de Rham differential. That's the Q I was talking about before. And I is this hopefully familiar term involving the Lie bracket on G. And the action functional in this case is exactly the Chern-Simons action. So here the derived critical locus is describing the moduli space of flat connections on the 3-manifold. Here is just perturbative Chern-Simons. I'm working near the trivial G bundle. So an example is related to string theory and gravity. Unlike this example, which is the simplest sort of topological gauge theory, the most natural sort of BV formulation does not result in a shifted symplectic structure. But what I'll try to explain today with a few examples, you oftentimes have a P0 space still. So every shifted symplectic space is P0. This is, by P0, I mean a space whose functions are equal with a degree 1 bracket. Like I had said, like any shifted symplectic structure gives you, -1 shifted symplectic structure gives you. But this bracket could be degenerate, could arise from a degenerate bivector, shifted bivector on your space. So there's no, I'm not demanding any non-degenerate condition. So let me explain basically some manifestation of why you would maybe want to weaken this non-degeneracy condition. And these are examples that come very naturally in string theory. So what I'm about to explain is relevant to what are called branes inside of an elaborate theory called M theory. And the branes here are supported on 6-dimensional manifolds. So these are going to be related to theories on certain 6-dimensional manifold. So first, let me take the six-dimensional manifold to be Riemannian. To be Riemannian. And the sort of primary field in this model here is going to be what I call a chiral, or what Witten calls a chiral two-form. So chiral does not refer to any complex structure here. It refers to the condition that the two-form satisfy this equation right here. So in other words, the two-form be, the curvature of this two-form be self-dual. And notice that if I were to attempt to write down maybe a standard-looking action functional that you see in Yang-Mills theory, you're going to fail sort of dramatically in this case, because the norm squared of B, which is, and here I'm just using the L2 norm, dB wedge star dB is just 0 for such two forms. So you sort of fail dramatically to write down a sort of the standard sort of action functional.
I thought star squared was -1.
Yeah, that's fine. What's the problem? So here's a chiral two form.
Well,
So
how can dB, star dB be dB if star squared is -1? The best normalization.
yeah, I mean, I could look at anti-self. I could look at star dB being minus dB2 and get a similar.
No, because star squared is -1. If I'm not mistaken.
Oh, sorry. Yeah, sorry. I should have a sign here.
There should be an I.
Yes.
Is B a complex form?
Yeah, let me take it to be complex. I'm sorry. Yeah.
It's complex, and then the definition of chiral has to have an I, no? I mean, unless I'm completely confused.
I think you're right.
Squared is
right.
-1.
You're right. Yeah.
Yeah.
There's a normalization that's wrong here. Yeah.
So there is a complex structure on wedge 6. I'm sorry, on wedge 3 of
That's right. Not on the six manifold. No. Yeah.
Yeah.
I'm trying to. Yeah. Thanks. So, yeah. So if you're to start to try to develop a sort of gauge theory for this two form, one natural complex you should write down is this. So I'm working in the BV formalism where this two form, this equation right here involves the curvature. In this case, it's just the differential applied to B. Of course, that differential, this equation has a lot of gauge symmetries, and I'm not going to say too much about it. But that's what results in these two terms on the left. So here I can shift the two form B by D of some one form, and I could furthermore shift that one form by D of some function. And this differential from degree 0 to 1 is encoding this condition that it be self-dual, so closed for D plus. So it turns out that this space right here is naturally a -1 shifted presymplectic space. And I'll say a few words about what that presymplectic structure is in a minute. But I'm going to be more interested in a related complex, which I just obtained by, which is related, it receives a map from this thing. And this thing is concentrated in degrees 0 to 3. And it starts with the 3 comma minus forms. Here I'm using the Riemannian structure. You should think about this F here, this 3 comma minus form, as being the part of the curvature of this two form here. And then I'm imposing some equations of motion. And I don't want to say too much about the rest of this complex here. But the point is that this thing on the right-hand side has a shifted Poisson structure. So X here is a P0 space. Here's X. So it's the thing concentrating degree 0 to 3. You can write down this degree +1 bivector very explicitly. So this is just a constant coefficient thing. I'm in a linear space. It looks like you just take the delta function, thinking about that as a differential form on the tensor product of this space with itself, and you apply this de Rham operator to it. So hopefully from this formula here, it's clear what I mean by degenerate here. In a typical symplectic theory, the symplectic form cannot involve derivatives necessarily. So there's going to be a very large degeneracy here of sort of fields which are sort of in the kernel of this bivector. And I could write down a similar formula for the shifted presymplectic structure here. Here, the pairing is just given by basically wedging and integrating alpha d alpha. Sorry, b db. And I'll say a few more words about what that looks like explicitly. So what's the context here? So this chiral 2 form is a fundamental field in this sort of physics context that I just mentioned, which is called 6D n equals 1, 0, or 2, 0 supersymmetry, supersymmetric theory. In such a theory, one is sort of tempted to construct a non-local action functional, being the sort of replacement for that action functional that was just 0. But this non-local action functional, it's non-local because of the appearance of this del inverse or this D inverse. And this D inverse is related to the fact that my Poisson tensor involves a derivative. Sorry, there's a glitch. Okay. So there's a holomorphic version of this. This is why I was emphasizing chiral did not mean there was a complex structure in that example, but now I really want to think about a complex structure on the 6 manifold. And it's pretty analogous to the example I just talked about. And this is going to be a situation I'm going to be more firmly in for the rest of the talk. So X here is going to be a complex threefold. Then I'm going to consider a resolution for the sheaf of closed 2 forms. So this is related to the model that Tony wrote down in his talk for closed 2 forms in a sort of more general derived setting. But even in complex geometry, I have a nice resolution for this sheaf of holomorphic closed 2 forms. Sorry, there should be a shift on this side. So I'm looking at 2 comma star forms in degree -1. So implicit in this is the entire Dolbeau complex corresponding to holomorphic 2 forms here. And in degree 0, I have a resolution for holomorphic 3 forms, again, using the Dolbeau complex. And I have a single holomorphic differential operator, just the de Rham operator from between degree -1 and degree 0. So it's just the sheaf of closed 2 forms with this weird cohomological shift. And the claim is that this thing is pretty naturally a P0 space. This P0 space has a explicit description, or the P0 structure, again, it's explicit. It's a constant coefficient bivector of degree 1. And again, it's basically just given by the Dirac delta function. Sorry, it basically just looks like you apply the holomorphic differential del to the Dirac delta function. So again, it has this non-degenerate or this degenerate sort of feature. And in this situation, you'd be tempted to write down an action functional in the style that I wrote down before. And again, you would find this sort of non-locality here. And this is due to the fact that, if I were to try to invert this thing, to write it as a symplectic form, which it's not, it's going to necessarily involve some distributional operator del inverse. So that's what appears here. I should say this is the same P0 structure that appears in approaches to topological string field theory of the closed B model via work of Costello and Lee. So using sort of mathematically formulating this BCOV action functional. This is another natural place where this action functional arises. So that's a very interesting interacting theory. Here I'm just studying, if you like, a free theory, just a quadratic term in the action. But nevertheless, it shares a lot of these features with the closed B model. So I just wrote down some P0 spaces. What are some explanations for this? So there's one explanation that I don't want to spend too much time on for the rest of the talk, but I want to say a few words about it. So roughly, you should think about these P0 structures as maybe one way they arise is from shifted presymplectic structures. That's sort of how I wrote the first example anyway. And you should think about a shifted presymplectic structure as a field theory that possibly has some constraints in it. So this is an analogy with sort of classical mechanics. One way to understand presymplectic structures is as you have some classical mechanics with a phase space that's symplectic, but you're looking at some submanifold there, some submanifold characterized by some constrained system, describing some constrained system. And by pulling back the non-degenerate 2 form, you'll get a closed 2 form still, but it may be degenerate. So there's a shifted version of this. So here you would start with some BV theory that's shifted symplectic, and you want to apply some constraint that's like considering a theory which maps to it. Oftentimes it's just like a subspace if you're in this sort of simple linear setting like I wrote before. But you can, if you have this sort of master BV theory in mind with this constraint, you can again restrict and get a shifted presymplectic structure. So here the shifted presymplectic structure arose from thinking about B as a chiral two form. So there's a sort of bigger BV theory here, which is like studying harmonic two forms. And this presymplectic thing that I wrote down before, you can understand as being a sort of constraint on a harmonic two form. And actually the same theory of harmonic two forms, which is non-degenerate BV theory, also admits a constraint which reveals the holomorphic example that I wrote down as well. So that's this theory of just a holomorphic closed two form. And these are the equations of motion for that holomorphic. These are the constraint for that, for being a holomorphic closed two form. And the P0 structures I wrote down are in a precise sense a certain reduction of these shifted presymplectic structures. So in ordinary presymplectic geometry, if you look at the kernel of the presymplectic form that defines some involutive distribution, and you can look at the leaf space of that involutive distribution, and in nice cases, if it's smooth, it'll have a Poisson structure. So there's a similar version of that here, which reveals these shifted Poisson structures. Sort of more, what I want to stick to more closely in the rest of the talk is the interpretation of these P0 spaces as arising from boundary conditions of a certain 7-dimensional theory. So that's related to stuff that Pavel mentioned in his talk. So the point is that the phase space of any theory has a natural symplectic structure, zero-shifted symplectic structure, and Lagrangians in a zero-shifted symplectic structure are canonically equipped with a shifted Poisson structure, a -1 shifted Poisson structure. And I'll spell out right now how each of the examples I just gave can be understood as certain Lagrangians in the phase space of a topological 7-dimensional theory, which describes flat two-gerbs, flat abelian two-gerbs. And you think about flat abelian two-gerbs sort of concretely as like Chern-Simons theory, but for a three form in 7 dimensions. So near the trivial two-gerb, I'll just do something perturbative. This theory is described by just three forms. So I'm looking at the full de Rham complex to encode all of the gauge symmetries that you have, just like in Chern-Simons theory. I'm shifting everything down by 3. So in degree 0, I had a 3 form like I promised. And the action functional is just given by the sort of standard kinetic term that you have in Chern-Simons theory. I don't know what a non-abelian two-gerb is, so I'm not going to write down the non-abelian theory, but this is what I can do in 7 dimensions. So I want to look at the phase space of this. So I want to choose a decomposition of my 7 manifold. In the Riemannian case, I want to choose a Riemannian 6 manifold times the real line, or the positive real line. And in the complex case, I want to choose a complex threefold times a positive real line. And the phase space in both of these examples, sorry, there should be a 3 here. The phase space in each of these examples, just via the sort of obvious wedge and integrate pairing, is a symplectic space, a zero-shifted symplectic space. So just in degree 0, for instance, a 3 form will pair with a 3 form, and you can integrate that. Or wedge with the 3 form, you can integrate that 6 form. And this zero-shifted symplectic thing has 2 Lagrangians, one determined by the Riemannian structure you fix on M, and the other determined by the complex structure you fix on X. And these are the complexes I wrote down before. So in the holomorphic case, which I'll pay more close attention to, you see the sheaf of holomorphic closed 2 forms appearing as a Lagrangian inside of here. And the claim is that the induced Poisson structure is exactly the one I wrote down just a second ago. Great. So this thing is a very nice shifted Poisson space. Its connection to physics is that it describes sort of an avatar of this chiral 2 form. I'll be more precise the sense in which it describes the chiral 2 form that I wrote down before, which was more natural from the point of view of Riemannian geometry. It's related to what's called a twist of the 60 supersymmetric theory, which is a simplification where the 60 theory, which a priori depend on some Riemannian Lorentzian structure, just depends on the complex structure. Great. So why do I care about P0 structures as opposed to presymplectic things, say, or some other exotic shifted structure? Well, it's because I have a mechanism for studying quantizations of these things. And the slogan I want to maybe justify briefly is that Batala and Volkovitsky quantization is like deformation quantization for P0 algebras. So the P0 algebras here are the algebras of functions you have in a P0 space. Yeah, so let me give an example. So my favorite example of a non-symplectic Poisson manifold is G dual with its Costan-Kirillov Poisson structure. And deformation quantization is the thing that produces the enveloping algebra. Hopefully we all know that example. So here, deformation quantization is like forgetting an associative algebra, classical limit of an associative algebra being a Poisson algebra, which in this sort of terminology is P1. So similarly, with the same exact Poisson bivector, if I what looks sort of artificial, if I just shift G dual, place it in degree +1, this thing is automatically a P0 space. And there's a shifted version of BV quantization that produces another sort of natural object in Lie theory. And that's called the Chevalier-Eilenberg homology, or the Lie algebra homology. And at the cochain level, it's the Chevalier-Eilenberg complex, sort of concretely. And as h bar goes to 0, so here the sort of deformation quantization parameter appears in the differential, as opposed to the associative case where the h bar will appear in the product here, the commutator. And as we take h bar to 0 here, I'm putting h bar in explicitly, you obtain functions on the shifted Poisson space. In the sense that in which this is a quantization, more generally involves finding this BV operator delta. Here, delta is exactly the Chevalier-Eilenberg differential. Great. So let me say maybe my main result. So there's a sense then in which I can study quantizations of this object here. So this P0 algebra that I just wrote down associated to this 60 theory, the claim is that it admits a BV quantization in a very similar way to this quantization of this sort of shifted version of the Costan-Kirillov structure. And taking into account locality on spacetime, Costello and Gulliam show that any such field theory gives rise to a factorization algebra. And at the classical level, what we have is a P0 factorization algebra. And I can quantize this factorization algebra to get a new factorization algebra. So maybe I'll just leave my result like that. The quantization of this P0 factorization algebra exists. I can write it down explicitly as a complex three-dimensional factorization algebra, and it shares a lot of beautiful connections to some cool geometry. So for instance, there's a further deformation of this thing, which is related to the Heisenberg vertex algebra, the GL1 Kac-Moody algebra, which gives in part sort of a direct field theoretic description of this story of Nakajima and Gorniatsky related to the AGT correspondence in physics. Yeah, so I'll stop there.
So any questions?
Thank you. Thanks, Brian. So one quick question about the two-gerb example. So when you mentioned that that in the non-abelian case, then it's not clear geometrically. Is it still true that it's a P0 space? It's just like the geometric interpretation in terms of two gerbs is missing?
Yeah, I just don't have a description that I can work with, sort of.
Okay.
Yeah.
But the P0 structure will be, I mean, even for like non-abelian.
In principle, like you, I mean, so finding this abelian version that I was talking about sort of fits into a family of proposed six-dimensional theories, which also depends on some non-abelian Lie algebra of type ADE. And you might want to venture to guess that there's a seven-dimensional theory associated to a Lie algebra of type ADE for which this thing is a boundary condition as well.
Okay.
I don't know if that's true.
Okay.
That's sort of like, yeah, exploratory work in progress. Yeah.
Okay. Thank you.
Yeah,
Thank you. Any further questions? More questions? Anything on Zoom?
No questions on Zoom.
Okay, then let's thank the speaker again.